Sir, please unmute yourself.
This,
Yeah, please, sir, start.
the screen sharing option is not coming. Hello, sir. I'm audible. Yes, sir. Now it is coming. Hello, sir. I'm audible. Yes, sir. Now it is coming. Sir, whether the screen is visible? Whether sir, the screen is visible?
Yes, sir.
Okay. So here we'll be starting the strength of material first, and we'll try to see the solution. Yes. So if you see the strength of material weightage and all, so here in this year, we basically they ask 1 mark question. That is a number of question were 1, and the 2 mark question were 5, right? So the total marks allotted to this section will be 11 marks, right? Now, so this is our question number 1 for this strength of material. So all of you can hear me properly. Sir, I'm audible. Hello, hello.
Yes,
So,
sir, you are audible.
yes, sir. So now when you read this first question, what they have mentioned, the following statement. This is the MSQ question. Now, so when you see here, which of the following statement is true about the state of stress in a plane? So they have mentioned the magnitude, the maximum or major principal stress is algebraically the largest direct stress at a point, right? So now this particular thing will be correct, right? This statement is correct, right? So basically, when we just used to find the principal stresses, you know, the major principal stress or basically maximum or minimum principal stress, what we used to write, we used to write something like this: sigma 1 and 2, we will be writing here sigma x plus sigma y by 2, right? Suppose a material is being subjected to sigma y and sigma x plus or minus under root of sigma x minus sigma y by 2 whole square plus tau xy square, right? So now here, if you observe very carefully, they have very clearly, right, we will be finding what? Two values, right? We will be finding the two values here, sigma 1 and 2, right? So you will be getting, suppose, two answers, right? Suppose you will be getting what? Two answers. Let's suppose, for example, you are getting the answer as 140 and suppose 180 megapascals, right? So according to definition of the principal stresses, the larger, right, the plus sign gives the larger, algebraically larger principal stress, right? Whatever the plus sign will be there, that will give you the larger principal stress, right? So sigma 1 will be 140 megapascal, right? And whatever the minus sign will be there, that will gives you algebraically smaller principal stress value, right? So maximum or major principal stress is the algebraically the largest direct stress at a point. That is a correct statement, right? Algebraically means mathematically wise we have to see, because on a scale when you see plus 1 minus 1, right? So according to mathematics, minus 1 is less than 1, right? Mathematics wise, right? Or I can take the example of minus 2. So minus 2 is what? Less than 1, mathematically, algebraically, right? So we have to define the principal stress on the basis of that. This all the things are given properly in the Gare book, right? So A statement is correct. Second statement, the magnitude of the minor principal stress cannot be greater than the magnitude of the major principal stress, right? So you can see here I have given one example where we are getting what? Minus 180, that is a minor or minimum principal stress. The most negative value will be, that is the most minus sign, the most minus value will be what? A smaller principal stress, right? So here if you just see the magnitude wise, So 180, what, minus 180 is what, greater than 140. So it can be greater than, so this statement is not correct. The planes of a maximum shear stress are inclined to 90 degree to the principal axis. Again, that is not true, because if we draw the Mohr circle, here tau, here sigma. Suppose I am getting Mohr circle something like this, for example. For the uniaxial loading case, suppose for example I am getting this one, right? A material is being subjected to sigma, that is a uniaxial tensile basically stress, right? So here I'll be getting what? This will be, what is my reference plane? This will be my reference plane, right? So from the reference plane, right, this is a maximum principal stress plane, that basically what? For example, this is C, this is A, this is B. So CA plane is what? Maximum principal plane. Whatever this plane is there, that is CD plane, will be what? Maximum shear stress plane. In a Mohr circle, it is what? 90 degrees. So in actual, it will be 45 degrees, right? At a 45 degree, that will be maximum shear stress will be acting, right? The normal stress, you know that the coordinates, if you see the coordinates here, or this CD and this C, both are what? Both are maximum shear stress plane, right? Both are maximum shear stress plane. So on both the, if you see the coordinates of D, what we are getting? Sigma n star into tau. Here also we'll be getting what? Sigma n star into what? Tau, right? So only direction will change because of what? Shear stress, maximum shear stress value. Sigma n star will remain same, sigma 1 plus sigma 2 by 2, or we can also write sigma x plus sigma y by 2, right? So normal stress along the planes of a maximum shear stress are what? Equal. A and D, this particular, for this question, AD will be correct. Getting my point? Tell me guys.
So guys, we
All of you are
know
getting my point? Can I move to the
the
next question?
normal stress on the plane of maximum shear stress is nothing but center of Mohr circle. So the center of Mohr circle is sigma x plus sigma y by 2.
Okay,
So
fine.
D is the correct answer, as well as A is the correct answer.
Now, when you see this particular next question, which of the following statement is correct about the elastic, basically what? Flexural buckling load of the columns, right? So whenever we see the buckling load, so what is the buckling critical load we have? N square, right? Pi square into EI minimum divided by what? Alpha square L square, right? Where alpha depends on what? End condition, right? What is the boundary condition? Whether it is a fixed column, or fixed pin column, pin column, or what? Fixed end, and one end is what? Free. So definitely it will depend on what? The boundary conditions, right? C will be correct, because based on the boundary condition, you will be getting what? Different values of critical load. For some types of beam, that just like a fixed beam, you need to apply little bit more amount of buckling load. So definitely it will depend on the what? Boundary conditions. Buckling load decreases with the increase of the length, right? But here they mention increases, so that is wrong. So when you see the option number A, the buckling load increases with the increasing flexural rigidity. What is the meaning of this? EI. The flexural rigidity, right? The flexural rigidity of the column will be what? It will be directly proportional, right? So if this will increase, this we have to apply more to buckle it, right? A will be correct. Now C is also correct. Now the confusion will be arises. A and C, most of you might be corrected, right? But all of you might be having the doubt in D option, right? Here they mention buckling load is not directly dependent. Yes, this statement is also correct, because indirectly, yes, indirectly it will depend on the density of the material which is being used, right? So we have some basically what? We can prove it by some taking some example. Here you might be thinking moment of inertia, right? When you think of moment of inertia, we can write moment of inertia as area into k square, right? So k, that is the radius of gyration, can be written as I minimum divided by a. This can be written like this, right? So k is what? Radius of gyration. The radius of gyration we can write what? I minimum divided by a. Now, what the moment of inertia? Can the moment of inertia or basically area will depend on what? The density. It might be possible. Let's say, for example, you have the mass of the basically column, which can be written as volume into density, right? For example, mass further, that is the mass of the column cannot be changed. When the mass of the column cannot be changed, so what we can write? Suppose length is also fixed. So we can write area into length, that is the volume into density, right? So here length is also fixed, mass cannot be changed. So what I will be observing here, that area into density will be constant. So maybe area will depend on what? Density, then only the product will be constant. So if this will also be depending on what? Density. So overall moment of inertia can change indirect way, right? Directly we cannot see. So I think according to me, D should also be correct, right? Getting my point, all of you. Yes. Now when you see this, already we have seen basically in memory based solution, some of the question we have already discussed. So the same answer will be there for this question also, what we have discussed, 0.9. The thickness of the uniform circular shaft is basically what? The thickness will be given as outer radius minus inner radius, right? The ratio of the inner diameter to outer diameter, right? So R1 divided by R0 they have given as 0.5. So D1 divided by D2 will also be what? 0.5, right? So this particular question we already solved. So once again I'll be solving this. Now when you think of this, so here we have to do yes, so here we have to do analysis based on the exact one and approximate one, right? So exact analysis first of all we will do. So they are asking what is the ratio of the maximum shear stress, that is based on the actual one, to the maximum shear stress according to thin wall approximation, right? So what will be the value? Tau, we know that T into R, maximum tau will be R maximum divided by J, right? So here what you try to think, T and R will be fixed for both the case, right? If I take the case thin wall approximation, thin wall approximation, here if you just take the thin wall approximation, so here you might be getting what? Once again, tau maximum T into R maximum divided by J. That is a different matter, that R maximum we used to write R minimum, mean value, right, for the approximation case. So here I'm just taking the value as equal to R maximum, right? Only J will change, J approx and J exact. So this will be changes to what? Exact, and this will be changes to what? Approx, right? So further if I solve J exact, what is the J value? Polar moment of inertia, right? Polar moment of inertia. So what is the J exact value? J exact value you might be knowing pi by 32 d naught to the power 4 divided by minus d1 to the power 4. So here we can write pi by 2. Now further we can simplify pi by 2. Again we can write a square. Again you can again you can just what? You can split into a square minus b square, that is a minus b, a plus b, right? So here you can write r square, and this can be written as Now here what you can write further, this will be pi by 2. Now r naught square plus r1 can be written as 0.5 times of r naught, right? So 0.5 times of r naught whole square. R naught square, what is the r naught square? R naught minus ri. Once again we can write r naught plus ri. R1, whatever the ri is there, we can write 0.5 times of r naught. This we know t, thickness, right? So what we can write, pi by 2, 1.875 r naught cube into t. This is my j exact. So if we further solve it, you will be getting, I think, 2.945, right? 0.93 into pi. So 2.945 we will be getting into r naught cube into t. Now once you got this value, what you can further write? J exact you got it, right? What is the j approx? 2 pi rm cube into t. What is the rm? R1, that is the mean radius. R1 plus R2 by 2. So here we can write R0 plus R1. What is the R1? That is, once again, inner radius will be what? 0.5 times of R0, right? By 2. So that is 0.75 times of R0. So here if we just write 2 pi 0.75 R0 cube into t. So this will be further can be written as 2.6507 R0 cube into t. This is J approx. Now once we got J approx value, what we can keep it? We can just keep the value what? Into the tau formula, right? Tau exact we need to find divided by tau approximate. And we know that T and R, that product in the numerator, that will be constant, only polar moment of inertia will change, right? So this will be J approximate, J exact, because that will be inversely proportional, right? So J approx we know 2.6507 and this is what, 2.945. So what you will be getting 2.6507, 2.945. So you'll be getting exactly 0.9. So this will be the answer for tau exact divided by tau approximate. Right? Check it out. We have to round off to one decimal place. So this will be the right answer, I think, 0.9. So how many of you are getting the answer? Can I move to the next question? Can I move to the next one? Now, Rohit, what is your answer? Okay, so basically most of you might be stuck with this question, as we have basically I was expecting some little bit on the higher side this question, but we already solved this particular problem in our basically classroom. So there was no difficulty because they have clearly mentioned the rigid bar, right? So this problem is not belonging to bending, right? So no bending will be considered in case of beam, right? Because they clearly mentioned it should be rigid one. So it will be totally what, just like this, it will be rotated with the angle theta. There will not be any relative deformation will be permitted in the beam, right? Now, as we might have discussed in the memory based solution, right, that was a good question as compared to this one, right? There we have mentioned the ei value, right, of the beam, but here ei will be what, infinity value, because it's a rigid one. So I cannot be infinity, so definitely E will be infinite, right? For the basically, what is the stress versus strain diagram? what will be the stress versus strain diagram for the what? Perfectly solid body or rigid body. That will be straightened, right? So E value will be what? Infinite. So that is what they try to mention, right? EI will be infinity, so the bending will not be considered, right? Now, here a rigid bar AB is subjected to uniformly distributed load of W, that is what? 100 Newton per meter. As shown in the figure, the bar is supported by the rod CD with ACD as a pin joint. The rod CD has the axial stiffness of 40 Newton per mm. The vertical deflection at the point D, they are asking, right? At this point, they are asking what will be the vertical deflection. So definitely when this will be rotated, right, like this, so definitely there will be some deformation will be there in CD, right? So they are asking this vertical deflections, right? Now, so here we can solve this problem. Whenever this type of problem will be there, you better try to draw either by the displacement diagram, whatever the deformation diagram is there. But deformation diagram we'll be discussing in our full course. That is also one of the very beautiful method by means of which you can solve any number of problem. But for that you need some expertise, and you should have a good number of accuracy, a good number of problem you must be solved before solving by that method, right? So blindly you can solve this question by strain energy method, right? Now, so in this one, what will be the strain energy for the strut? Because strain energy for AB will be zero directly, right? Because what is the strain energy of the beam? Generally, if the bending will happen, m square length of the beam divided by 2EI. This will be what? Infinity. So this will be zero. So only the strain energy will be there because of what? CD bar. What is that? P CD square dx divided by what? 2A, right? Because they mention the axial stiffness, so axial strain energy will be considered, right? 0 to L, that is the length of the rod. You can consider the length of the rod as L rod, right? So I am here mentioning AE by L. What is the axial stiffness? You might be discussed, you might be knowing in the vibration also, right? So that they have given us 40 Newton per mm. Now, when we proceed with this data, so we have to draw the free body diagram. First of all, what will be the free body diagram? Here, that is force CD will be coming. Now we need to find the vertical deflection, right, at the point D. And if you observe very carefully, FCD is an internal force, that is not the external force. So we have to apply some virtual load. That virtual load, after the, what is the formula? Deflection at point D, the total strain energy we have to partially differentiate with respect to what? Load P, and at the end P has to be equal to 0 because that is the virtual load, right? So now when you think of this solution, here load is what? Uniformly distributed load of W. Here I'm just writing it as L. Length, I know that that is 1 meter, but I'm keeping it as W and L in the form of W into L, right? So here, what is the moment about A? Moment about A should be 0. So what I'll be writing? W into 2L, that is the anticlockwise movement, minus that will be with that side, P into what? L. And what about W into 2L? That is a load. But at what particular length it will be acting? At this centroid, right? So that will be L once again. P into L plus FCD. This particular component will be what? FCD cos 45, right? If this will be 45, right? So FCD cos 45, that is root 2, once again L. So here we can write FCD. FCD can be written as root 2 2W minus P, right? That is 2WL. Minus P. So 2 root 2, that is WL minus P root 2. Now here, once we know FCD, that is a force which is being acting on the strut member, right? CD member, whatever the force is there, that will be acting, right? Now, so here what you are understanding, what we can write, strain energy in the what? Rod, that will be, that can be written as FCD square. Directly we can write, because that is not the function of X. So FCD square into length of the rod divided by 2e. FCD square, what is FCD square? 2 root 2 W into L minus 2 root 2P whole square divided by 2 A by L, that is for the rod, right? So now when you just do squaring, that is what? 8 W square L square plus 2P square minus what? 8 WLP divided by what? 2A by L. Now what we have to do, we have to differentiate, right? For finding the deflection at point D, we have to differentiate with respect to the load which is being acting on the point D, right? So if I just do the differentiation, dou U divided by dou P, so what I'll be getting, this will be 0 if I just do the differentiation. 2P square, that will be 4P, right? Ultimately P will be 0, so that will also be gone. Minus 8W into L, dou P by dou P, that will be 1 divided by 2A, that is the length of the that is what? Axial stiffness of the rod. So axial stiffness, that is a deflection at the point D, will be what? 4WL divided by A by L. So 4 into what is the W? That is 100. Length is 1. A by L, they have given 40 Newton per mm, right? Newton per mm. So convert in terms of what? Meter. All the units in meter. So you'll be getting final answer what? In meter. And finally you have to convert to mm, right? So 4 into 100 into 10 power minus 3 divided by 40 into 1000. So you'll be getting what? You'll be getting 0.01 meter. 0.01 you can write, or you can write 10 mm, right? So how many of you are getting this particular answer? Any one of you are getting the answer? Yes. Tell me guys. Any one of you are getting the answer? Can we move to the next question? Fine. So maybe here and there we will see the what will be the final answer, but this we are giving the solutions that has to be correct, I think. Round of 2 nearest integer they have they have mentioned, so the 10 will be correct. Let's see now. So this question, when you think of regarding the what bending moment, they ask a cantilever beam of the length 2a is loaded at the tip with the force F as shown in the figure. The beam is subjected to supported in the middle. That is I mentioned in the on that day, that is a memory based solution we have given. There I mentioned that it is a propped overhang beam, right? Two types of propped cantilever beams are there. In one case, the whatever the propping is there, or whatever the support we are providing to reduce the deflection at the ends, or maybe in the somewhere at the ends, somewhere in the middle of the ends and initial points, right? So this is one of the case where it is being fixed not at the ends. That means it is not, support is not placed at the ends, it is in between, right? Now, so magnitude of the moment reaction at the built end is alpha into Fa. So here what you can just take, you can write it as, you can convert into equivalent diagram of like this. So whatever the F is there, you transfer this F to this point. This is a point A, point B and point C. You transfer the load P. When you transfer the load, any load to any point, what is the method we have discussed? You just apply two loads of equal magnitude, right? sorry, F, this will be F. So this F will be coming downward, there is no doubt, and this P, this F and this F will create the moment about which point? This one. So this will be F into A, right? So now we know that this is the combination of the three cases. This is the combination of the three cases where this beam is subjected to what? Three kinds of load. One will be support reaction at B, that will be upward deflection, right? This will be deflection 1. Then there will be deflection which are acting in the downward directions because of what? P. This will be deflection 2 minus this will be deflection which are happening because of movement, that is F into A. Once again this will be going like this. So that is the deflection 3, right? Net deflection at the point B has to be 0. The net deflection at the point B has to be 0, right? This principle of superposition method we have discussed very clearly in our what classroom courses, right? No need to find the value by modify Maclaurin method or taking the section and doing the double integration method and all, right? Putting the what a condition, boundary condition value, that will be again very lengthy, right? Now, so here deflection 1 minus deflection 2 minus deflection 3 has to be 0. So what is the deflection because of the point load for the cantilever beam? We know that, right? That RB into AQ divided by 3EI. Deflection due to point load P will be what? AQ minus 3EI. And because of the movement, we know that, right? Deflection because of the movement for the cantilever will be what? MA square divided by what? 2EI, right? So that will be M is what? F into A cube divided by what? 2EI. That will be 0. So here, if we just calculate, P is nothing but F only. So I'm writing here F, right? Now, so what will be the final formula? RB in terms of F, that will be 5F by 2. Check it out, whether you're getting 5F by 2 or not. So once you get the value, RB value, now you know the RB value, right? So this cantilever beam, we know that this is 5F by 2. This is F. So what is the moment about A point? Bending moment about A point? 5F by 2, that will be sagging bending moment. So 5F by 2 into A minus F into 2A. Even though you are basically not knowing the sign convention, so no need to worry because they have mentioned magnitude only, right? So 2.5 FA minus 2 FA. So that will be 0.5 FA. So this is what alpha we have, right? So the answer will be what? 0.5, right? Getting my point? So can we move to the next one? Tell me, guys. What is the answer? Is it correct? Just check it out. Now, so now when we move on to this particular question, consider a thin wall pressure vessel which is made up of alloy with the yield strength value, right? Yield strength value they have mentioned that is 300 megapascal. That is, now some of you might be confused in the wording of this question. Not many of you, but some of you, those who have not enough practice, those who are not aware of the material, or maybe they might be not aware of the this theories of failure. So some of you might be confused. Yield strength, whatever is given, that is in tension or shear, right? So generally, one might says, what is the formula we used to write? Sigma YT by factor of safety. That what we used to write, half of sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square, right? Check it out. This is what the formula we used to write, right? Now in this one, again, what is the value of sigma 3? That is the radial stress. Until unless in gate examination they mention to take the radial stress as minus p, we usually take it as what? Zero value. So when you put sigma 3 to be 0, so you will be getting what? The formula in terms of sigma 1 square plus sigma 2 square minus sigma 1 sigma 2, that is sigma y by sigma yt divided by 1. So from here formula only you must be knowing that sigma yt they have given in what? Tension, right? So sigma yt, that is 300 megapascal. Now sigma 1, what is the hoop stress? PD divided by 2T, right? Or in terms of PR divided by T. In the problem, they have mentioned the radius of vessel to thickness, that is 100, right? So 100 into P. And sigma 2 is what? That is a longitudinal stress. That is in case of horizontal cylinder, if I talk about the horizontal cylinder, not hanging one, right? If you just talk about the horizontal placed cylinder, at the ends, whatever the pressure will be acting, right, that will be uniformly distributed, right? That pressure will be, because there will not be any height as in case of hanging one, right? So here it will be half of that value, right? So sigma 1 by 2, so that is 50p. So when you put into this formula, sigma 1 square, that is what? 100p whole square, 50p whole square minus 100p into 50p. So here if you just calculate p value, you will be getting 3.464 megapascal, but they ask to calculate the value round off to 2 decimal places, so that will be 3.46. Check it out. Are you getting 3.46? Anupam, what is your answer? Yes. Anyone can confirm the answer? What are all the answers you guys are getting? Correct. Now, I think that's all from the strength of material point of view, right? So we have total how many questions? Total 6 questions were there, right? Correct.
So, sir, we will start vibration. Please share vibration. Yeah, before that, any doubt, guys? So, how much you are getting, Anupam? Yes, both. Yes, Rohit, that also rib and shear center. That is from thin wall structure. So Rahul sir's expertise is in strength of material and vibration. So we'll start vibration. Yeah. Thank you, sir. So strength of material was as usual around 11, 10, 11 marks. So last year they asked more. This time, Rahul sir, they asked gas dynamics more. Compressible fluid flow part was more this time. Yeah. So they are playing, every year now. But all the questions more of were theoretical from GD.